Okay, let's conclude this nice discussion on what the tropical Pacific SST gradient and the Pacific Walker cell have been doing so far, and how the models are not doing so well in capturing that. But the models are very gung ho about what will happen in the future in terms of their consistency. So now you have to understand whether models are correct in the future, even though they have been wrong in the past. This is very tricky, right? So you have to understand the feedbacks that are happening in the real world, in the models, and what they will do with continued increase in greenhouse gases. And then, of course, there are scenarios which add all kinds of uncertainties as well, but just take it as increasing emissions or emissions bending at some point and so on. And we want to understand whether the controls on the Pacific SST gradient and Walker cell are shifting from strengthening feedbacks into weakening feedbacks, so that models are probably capturing the right process into the future. Okay, so we looked at oceanic tunnel and we talked about SDCs and so on. We are in the dynamical constraints part of the SST gradient mechanism. As I said, energy budget constraints explain it differently, and dynamic constraints look for different feedbacks, but they have to be consistent because the answer is given by the observations, what happened, and you have to understand why that happened and how the energy budget will put constraints on what happened or why it happened. And similarly, dynamical responses and feedbacks also have to explain that. So this is the next step of it, tropical basin interactions. Did I already read that? I think I did, right? So maybe I'll just read it again. Tropical atmospheric I'm getting old, folks. Tropical atmospheric teleconnections that link ocean basins have also been proposed to play a role in modulating the PWC and hence the zonal SST gradients. I already mentioned this, so let me just continue. Observational analysis and modeling studies of varying complexity all suggest that relative warming in both the Indian and Atlantic basins leads to stronger equatorial Pacific trade winds and hence to an enhanced zonal SST gradient. So to re-emphasize, Atlantic and Indian Oceans are controlling the heat uptake as well, because if the trade winds strengthen and PWC strengthens, upwelling strengthens, then more heat goes into the ocean. These interbasin relationships exist on interannual and decadal timescales as well, and extend to include the response to human-induced warming. And this has been the way it's been stated by Richard Seeger, where he keeps saying global warming response will be La Nina-like, which means strengthened trade winds, cooling in the east as opposed to warming. And this is similar, that even on interannual to decadal time scales, the Indian and Atlantic Oceans behave similarly to the anthropogenic forcing in terms of the Pacific response. They are all related, but we keep saying Pacific response because that's the dominant player, right? Recent studies suggest that the pan-tropical basin interaction is underestimated in many climate models, and I already mentioned that. So let's jump ahead to ENSO-related processes. It has long been recognized that changes in the tropical Pacific climatological mean state can affect the characteristics of ENSO, such as its amplitude, pattern, and periodicity. So there is a east-west SST gradient. Thermocline is shallower in the east, deeper in the west. Trade winds, ITCZ sits there, and the background state is not always the same. The SST gradient may be weaker or stronger on decadal time scales, and there is ENSO clustering happening as well. So there are decades where there are more El Niños and fewer La Niñas, and there are decades where there are fewer La Niñas, fewer El Niños, more La Niñas, and the debate has been again about whether the duration, intensity, frequency of El Niños is responding to global warming, and if so, what it is doing. And then people jump ahead and say this is what is happening in models, and they will say this is what will happen, but we have to be careful about that, right? So, however, it has been suggested that changes in ENSO variability in turn affect the mean state through the nonlinearities in the air-sea coupled processes such as nonlinear dynamical heating. What it basically means is that ENSO variability, which is a clustering of ENSOs in different decades, affects the ocean basic state itself because you're constantly recharging and discharging heat. And if you have more El Niños, you may get a flatter, let's say a flatter SST gradient and so on. You have to be careful saying that, but still, you can imagine that the lower frequency rectification of El Niños and La Niñas themselves will appear as a climatological state when you do averages over many years or decades, right? Therefore, uncertainties in future changes of ENSO variance translate to uncertainties in the tropical Pacific mean state change. Although there is an indication that global warming will increase the number of extreme El Nino events, it is still uncertain how ENSO characteristics will change in the future. Okay, you will get a lot of papers saying what will happen. Very few have explained what has happened, even though there has been a warming and ENSO has shown clustering. We haven't necessarily explained exactly what happened or why it happened. Yet ENSO-induced rainfall variability will robustly increase in a warming climate regardless of the change in ENSO characteristics. So you can go and read the references on why that happens. So this can act to suppress the ocean upwelling in the central eastern equatorial Pacific through increased freshwater flux. So that comes back to PWC, evaporation response, precipitation response, SST gradient, and all the other feedbacks. Although this mechanism has not been verified for the historical period, increasing rainfall variability in the eastern tropical Pacific has been identified from recent observations, which provides an additional argument as to why one might expect weakening of the zonal SST gradient in the future. So just remember the many things we are saying. Models are doing many things wrong, including reproducing the observed SST gradient, but we are saying there are some processes which are correct in the model, hence their projections can be reliable. So you have to then go back and reconcile past and future changes. The above discussion highlights the mechanisms that act to either strengthen or weaken the zonal SST gradient and PWC, which we will see. We already looked at figure 4. Figure 3 we looked at. Where is my figure 4? Let me pause and then put figure 4 because I already screwed up. Okay, so when I prepare these things, I read the paper, I get excited saying, I want to report this paper as a podcast because it's such a nice paper, and then I have to prepare the slides to capture the main points, and sometimes I screw up and miss including a figure and so on and so forth. So I put the figure 4 in now. So we'll look at table 1 as well, which I have definitely included. So the above discussion highlights mechanisms that act to either strengthen or weaken the zonal SST gradients and PWC. Table 1 summarizes our assessment of how different mechanisms have contributed to shaping the tropical Pacific SST pattern change over the recent past, as well as its long-term projection. We emphasize that they are based on multiple lines of evidence, climate model simulations, theory, observationally constrained coupled simulations, often called pacemaker experiments. So even though the models, when run freely, are not doing so well, there are many ways to use the models to do kind of sensitivity studies. If you don't give it greenhouse gases, what happens? Obviously, we use that a lot in attribution experiments. And these so-called pacemaker experiments, let's read again what they mean here. So observationally constrained coupled simulations, often called pacemaker experiments, which means if your SST gradient is wrong in the tropical Pacific, for example, you nudge it to observations and tell the model, hey, you are going in the wrong direction, this is what you should be doing, and then see what it does when given this information. Okay, and there are emergent constraints, and more importantly, our fundamental understanding of physical processes, and altogether these are used to reconcile the past strengthening trend with the projected weakening of the zonal SST gradient in the future. So emergent constraints are basically what was constraining, whether it was more energy budget that was dominating or the dynamic feedbacks that were dominating, and what is emerging over time? Is it shifting the main control, which is the argument here? But you can see that they are also trying to say models are projecting a robust weakening of the SST gradient. Models haven't captured the strengthening gradient so far, but they are doing something right, so we are going in the right direction. That's the whole crux of this argument, right? So let's look at the schematic illustration of possible forced mechanisms for the tropical Pacific changes in the zonal SST contrast and associated trade winds, which relates to Pacific Walker cell. The processes operating in the atmosphere and the surface on the left and the ocean here in the right are shown separately. Red arrows represent the forcing processes, whereas the blue arrow indicates the past strengthening of the PWC. The background shading shows the SST and equatorial ocean temperature trends for 1979-2023, which is 2013, sorry, which is the strongest constraint we have in terms of what has happened, and we are just trying to explain why it happened and what will happen in the future, right? So tropical basin coupling, so Indian Ocean and Atlantic Oceans can feed back to what's happening in the Pacific. As we mentioned, aerosol forcing, even though I didn't read it, they have aerosol and ozones have a forcing impact on the coupled response. So coming from both directions here, the arrows directions don't matter so much, but it's a northern hemisphere process as opposed to the southern ocean impact that we looked at. So since the southern ocean is a channel and connects everybody, anything that happens here affects the cross equatorial transport, which affects the ITCZ, the trade winds, and the SST gradient, and the Pacific Walker cell as well. Okay, so this is nice schematic, and if you zoom in into the ocean on the northern hemisphere, including the tropics, then you have basically the mean state, but then you have amplified ocean thermostat response that I mentioned, where if global warming, which is trying to trap more energy, but the ocean responds by increasing upwelling here, then this is the place where heat can go into the ocean, so you damp the global warming rate, especially if you can keep the heat in the ocean and not release it all back to the atmosphere. And there is the oceanic tunnel, the subtropical cell that we talked about, on how anomalous advection of mean temperature versus mean advection of the anomalous temperature can have different responses and asymmetric responses hemispherically as well as zonally. So all these are important concepts. So let's read a bit more and then we'll look at the table. Where were we? Was I? Okay, yeah, I'm in the right place. I don't know why. Yeah. Given that the mechanisms explaining the future weakening of the SST gradient are robust, both in climate model projections and supported by our process understanding, there are three possibilities to explain its past strengthening. So now we are saying models didn't capture it, but this is what the future is doing, and that is robust. Hence, we have to explain the past as to why it's strengthened and why models fail to do that. Transient forced responses summarized above, large internal variability, and a combination of them would have probably misled the models because they didn't capture them. Many studies that analyzed large climate model ensembles have shown that the spread of the past SST and PWC trend patterns due to internal variability is larger than the difference of the forced responses across models, supporting the active role of internal variability. Whoa. What do we mean by that? Internal variability is all the natural variability, basically El Nino, monsoon, PDO, NAO, and so on. And if that is so strong that it can automatically, without any greenhouse gas forcing, produce various patterns of SST gradient and PWC, and if the models have failed to capture the impact of that internal variability, then they have just managed to miss what the nature did. So what nature did is one realization, but it could have gone the other way, and nature could have also weakened just like the models if the internal variability was different. Okay, That's a fair argument, but you have to make sure that models don't have systematic biases as well. They do, but you have to understand how that affects your future projections. Nevertheless, the multiple lines of evidence suggest that observed recent SST trends are in part due to external forcing. So we are all saying it's not just internal variability. As the first and second possibilities are not exclusive but can coexist, the most plausible hypothesis is the third one, namely that their combination explains the past strengthening of the zonal SST gradient and the PWC. So internal variability did contribute a lot to the realization of strengthened SST gradient in observations, but anthropogenic forcing has also contributed, and it hasn't managed to weaken the gradient as opposed to what happened by strengthening it. Although definitive evidence has not yet been provided, our current understanding of the physical mechanisms reviewed above suggests that the strengthening mechanisms have been efficient in the recent past, whereas the weakening mechanisms that will dominate at large global warming levels have so far been less efficient. So now we are saying something new. The global warming has happened, SST gradient has strengthened, and there has been a positive feedback. But as we increase global warming, other processes will begin to dominate, and hence the SST gradient will weaken, which is what the models are doing. Hence, models are correct for the future. This narrative reconciling the past and future SST pattern changes in the tropical Pacific is testable in future studies, and we cannot rule out the possibility that the narrative becomes irrelevant if there are strengthening mechanisms that have not been identified and are severely underestimated in the current climate models. So you take the observations, you take data, reanalysis everything, you look for feedbacks, you also look at models, and it's possible that neither the data reanalysis models are giving us all the information about why the SST gradient has strengthened, and hence we may still be wrong. Resolving model observations discrepancy, then, attribution of the recent tropical Pacific SST pattern change and associated PWC strengthening to external forcing and internal climate variability remains a challenge, as the relative contribution of internal variability depends on the model's ability to represent the externally forced response adequately. The estimate may be biased if models do not represent the transient forced responses well. So as we are increasing greenhouse gases in the real world, the model has to keep responding to this radiative forcing, and maybe the models just are not doing a good job. There is also a possibility of internal variability being too weak in the models, which means they are not having enough amplitudes of El Nino, not enough events, not enough monsoon variability, which is true. They are all kind of little bit deficient in the models, let's say. Models are amazing. You give them energy at the top of the atmosphere and they do everything. They produce El Nino, monsoon, NAO, PDO, everything, but everything will be slightly different than the observations, let's say, okay? Remembering that observations also have deficiencies, they are not long enough, and so on. So it's of course possible. Indeed, a recent paleoclimate reconstruction suggests that the 1992-2011 PWC intensification was not unprecedented over the past 800 years, although this PWC intensification appears near the tail of the probability distribution, which means forcing may be important, increased greenhouse gases. The null hypothesis that the observed recent trend can be explained solely by internal variability still needs to be tested carefully, using, for example, an ensemble of long control simulations. Much focus has been on testing this null hypothesis on the basis of SST patterns. However, natural variations could be more easily distinguished from the forced response by looking at other climate variables such as the ocean surface temperature, ocean subsurface temperatures, and precursor patterns of surface fluxes. It's kind of how to diagnose whether we are right or wrong. So jumping ahead, as the global climate continues to warm, nature may give us an answer to the puzzle of the mechanisms leading to the tropical Pacific warming pattern change, but climate science should not wait for such changes to appear. Instead, should take action to improve models as well as to develop theory, diagnostic techniques, and attribution methodology for quantifying the physical mechanisms of the tropical Pacific warming pattern changes. So that's like saying we know a lot and yet we don't know a lot. So we have to do a lot more, which is a fair analysis, fair conclusion. Summary of existing mechanisms of the forced tropical Pacific response to uniform and non-uniform external drivers and their importance in the past and the future. So I'll take some time reading this since it's very important. So mechanisms here: direction for zonal SST gradient and hence the Pacific Walker cell. Role of the past, so possible model biases can affect the conclusions here. Role of the future, if the models are wrong here, then you have to figure out whether they are right here. And lines of evidences are shown here. Energy budget constraint on the hydrological cycle or anomalous GMS mechanism, right, as opposed to PWC versus GMS, right? So yeah, you can go back and look up everything we have said. Direction for the zonal SST gradient is weakening here. Evidence is inefficient, possible model bias is there, and role in the future is more important for energy budget constraints. Line of evidence comes from climate models, theory and process understanding. So see that we are still relying on models for a lot of the understanding. Differential evaporative damping, direction for zonal SST gradient in PWC is weakening and for uniform and non-uniform external forcing. Not identified in terms of the past role, but important for the future. So climate models, theory and process understanding help us there. Rainfall induced freshwater forcing, weakening, inefficient in terms of the role in the past and more important in the future. Climate models and process understanding. The evidence. Ocean tunnel is weakening for the future, potentially important. Role in terms of STCs that we mentioned, more important in the future. Climate models and process understanding gave us this. Forced ocean models have played a role in explaining STC STC contribution as well. Ocean dynamical thermostat strengthening in the future, potentially important for the past but underestimated by models. Okay, that's the model bias. Less important in the future. Climate models, observations and process understanding have helped us. I did some work on this as well with Richard Seeger that you can look up. Relative warming of the tropical Atlantic or Indian Oceans is strengthening in the future. Projections important but underestimated by models, remains equally important in the future. Climate model pacemaker experiments and process understandings have helped us. Aerosol forcing will strengthen the SST gradient in the future. It's been important and less important in the future. So climate models tell us this, which means you have to be really wary about it. Doing aerosol impacts is very tricky because they have direct impacts, indirect impacts, and direct impacts are of course blocking sunlight, etc. Indirect impacts are playing through microphysics, cloud properties, rainfall, droplet sizes, amounts, hurricanes, everything else. Okay, so it's very tricky. More data is not necessarily going to improve our understanding because there are fundamental processes that we need to understand. Maybe AI will help. Who knows? Southern Ocean cooling strengthening in the future. It's been important but not well represented in models. Reverses in sign in the future, and climate model pacemaker experiments and emergent constraints have told us this. And so nonlinear rectification, which is the low frequency impact of El Nino and La Nina, has been will be strengthening or weakening depending on what ENSO does, but we haven't understood it in the past yet. We get a lot of papers saying what will happen to ENSO in the future. I'm always skeptical about those, but important people write those papers. Important if ENSO skewness changes, so you have to figure out what that means, but basically ENSO is skewed in a certain way in its anomaly patterns that you have to go and see. Climate models and process understanding have told us this. So direction defines here the change in the tropical Pacific zonal SST gradient and the Pacific Walker cell. The importance of individual mechanisms in the past and the future was evaluated on the basis of the lines of evidence shown in the last column. Mechanisms are probably underestimated or not well represented in climate models as indicated by the brackets. Okay, so that's the last slide here. So do we need to clarify anything else? I don't know. Let me just scan to make sure I didn't miss something. ECS, we have explained pretty much everything. La 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 la. Okay. I'm just, because this is such an important topic, and anyway I have done 3 podcasts, I might as well take a minute to see if I have made, skipped anything that is actually important. Gross moist stability, GMS, we already talked about. Tropopause rising. Okay, so this is hopefully helpful, and the paper is amazing. You need to go and read it if at all this topic is of interest. My podcasts are basically meant to give you an introduction to what the paper is saying, make the most important points in my own subjective choice, but also to help people who are not technical experts, so that I try to explain it in ways that helps hopefully people who are not really deeply involved in this topic. Each topic tends to have a group of people who work on all the details of that, and Richard Seeger, Matt Collins, Sarah Khan, many people working in this direction. Okay, let me leave this here. See you in the next topic, which is PDO. So we'll look at Pacific Decadal Oscillation subsurface temperature driver. If that is not so interesting, then I will jump to a completely different topic and talk about recycling cement. Can we, cement is a highly emitting sector. We need to reduce emissions, but also if we can recycle it instead of producing junk, then we'll be better off. Okay, very different topic, but that's how I jump around in these new findings in climate change. Then see you.